Today we're going to be learning about right triangle trigonometry. But before we jump into that, I want to just introduce quickly the two main frameworks that we use for trigonometry. That would be right triangle trigonometry that we're going to learn today, or learn about today, and also unit circle trigonometry. Now, these two ways of approaching trigonometry are, in fact, very similar. They're just a different way of looking at it, and whether you use one or the other depends on the application, and so we're going to be focusing on both throughout this course. For right triangle trigonometry, let's draw a right triangle here, and we'll make this the right angle. So we have our two legs of that triangle here and here, and then we have the hypotenuse of the triangle, which is opposite the right angle. Okay, so we're going to label one of the other two angles as theta. Now, once we've labeled it, we're going to label the side that is, sorry, the leg that is touching that angle or makes up part of that angle is called the adjacent side. And the leg that is across from that angle is the opposite side. Okay, and then we'll just use the typical term used in geometry, which is hypotenuse, for that third side that is opposite the 90-degree angle. And we'll even label these as A, O, and H today. Okay, now with that triangle drawn, we can define our initial three trig functions. Now the trig functions are going to be functions on this angle here. So that means you're going to input the angle into the function, and the function gives you back a number. And that number is going to be a ratio of two of the three sides. So the first trig function that we're going to learn about is the sine function. As a function, it's written as sin, sin, but it's pronounced sine. And so sine of theta is going to be computed as the following ratio. You take the length of the opposite side and you divide it by the length of the hypotenuse of that triangle. So we'll say opposite over hypotenuse. The second trig function is the cosine, written as cos of theta, and that is going to be the adjacent side over the hypotenuse. So it's a ratio of two of the three sides, again, the adjacent side over the hypotenuse. Now the third one is the tangent function. We write that as tan of theta, and it can be also written as a ratio of two of the three sides. It's the opposite over the adjacent. And so we'll write that as O divided by A. Okay, so these are the three trig functions written in terms of the three sides, or of ratios of the three sides of a right triangle. Now, what unit circle trigonometry does is it just embeds this picture inside of a unit circle. So here's what I mean by that. We're going to draw a triangle, this time inside of a unit circle that's centered at the origin, embedded in the xy plane. Now, what we can do is draw a triangle that just touches that unit circle, and this is going to be how we define sine, cosine, and tangent using the unit circle. So we're going to write the angle theta right here again. This time, if we're looking at a unit circle, that means the radius of this circle is 1, and so the hypotenuse actually is going to have length 1 on the unit circle. And we're going to look at specifically this point right here and give it labels. This is going to be the point xy. Okay, this is our x-axis and our y-axis, and so we're just labeling this point with its usual coordinates. And now what we can do then is label the adjacent and opposite sides as x and y. So we have x for the adjacent side, y for the opposite side, for the lengths of those two sides. Now when we rewrite sine, cosine, and tangent, we can do that in terms of x and y. So first of all, we have sine of theta, and that is going to be given by the opposite over the hypotenuse. But here what that is y over 1, which is just y. So we have y is equal to sine of theta. The cosine, on the other hand, is going to be the adjacent, which is x, divided by the hypotenuse, which is 1. So we have x over 1 equals x. So cosine of theta equals x. And the tangent of theta is the opposite over the adjacent, which will now give us y over x. Okay, so these are the two frameworks that we're going to be using throughout the semester for defining trig functions. We have right triangle trigonometry, where we can have a right triangle with a hypotenuse of any length, and then unit circle trigonometry, where we need to have the hypotenuse be equal to 1, and we're viewing this as a triangle embedded within the unit circle. Whether you use one or the other of these depends on the application, and we'll be using both. Okay, before we go on, I just want to share a useful mnemonic for remembering these ratios. If we look at the first letter of our function here, and then OH, we'll write that as SOH. And then we'll move on to the second function. We look at the first letter and AH, so we'll have CAH. And then we're going to look at the first letter of the third, that's T, and then we'll have OA, so that's going to be TOA. So sometimes people like to remember these as using SOHCAHTOA. So SOHCAHTOA. If that's useful to you, great. That helped me remember it when I was a student. Eventually, you just kind of remember it because you use it so much. So I'm not sure what happened with our spacing here, but let's scoot this up right here. We're going to work on this example now. So find sine of theta, cosine theta, and tangent theta correct to 2 decimal places, and we're given this triangle. So here's our triangle for the example. We're given that this side is length 9, this side is length 5, and our angle is here. Okay, and then we'll label this third side the hypotenuse. And if we want to find all 3, sine, cosine, and tangent of that angle, that means we're also going to need to know the hypotenuse. So if we think back to our previous experience with right triangles, we know that we can find that hypotenuse using the Pythagorean theorem. And that theorem tells us that if you take the 2 legs of a triangle, a squared plus b squared, and then that's going to be equal to c squared, which is what? This is the hypotenuse of that right triangle, and these are the 2 legs. I apologize for my voice, getting over a cold here. So these 2 are the legs, and this is the hypotenuse, and this theorem is only valid for right triangles. So for us, 9 and 5 are the legs, and so to come up with the hypotenuse, we're going to say that the hypotenuse is, or the hypotenuse squared is what? 9 squared plus 5 squared. That would be what? 81 plus 25, which is what? 106. And so to get h, we're just going to take the square root. We don't need to do plus or minus because this is a length. And so we know it's just positive square root of 106. Okay, so that's the hypotenuse. We already know the opposite and the adjacent sides. So now we can write out sine theta, cosine theta, and tangent theta. So we have sine theta is, according to our right triangle trigonometry, opposite over hypotenuse. Now the opposite here is going to be what? We have our angle is right here this time, so we need to be careful because we've drawn this differently than we have in the past. So the opposite of that angle is going to be the length 9, and then that will be divided by the hypotenuse, which we know is the square root of 106. So we'll have 9 over the square root of 106. Now, we're supposed to round this answer to 2 decimal places, so let's get an approximation for that. We're going to do that using our calculator. All right, so we'll take 9 divided by the square root of 106, close those parentheses. This will give us a decimal approximation. We'll notice that we have 0.87. We're supposed to go to 2 decimal places. So we'll look at the 4, the next decimal place. That's less than 5. And so we'll just round to the 7. So we'll have 0.87. Now we'll compute the cosine of theta. That is the adjacent over the hypotenuse. And we can write that as what we have. The adjacent is 5 over the square root of 106. So going back to our calculator, we can compute that as 0.4856. The second decimal place is what we want to round to, so we look at the next one. That's a 5, and if that's 5 or above, we're supposed to round up. And so this is going to be 0.49. And again, I should technically use an approximation symbol there, because this is not an exact answer, this is an approximate answer. Okay, and now we have the tangent of theta, which is going to be the opposite over the hypotenuse, which is going to give us 9 divided by 5. And we can turn that into a decimal exactly. That would be, what, 1.8, and to 2 decimal places then that would be 1.80. Since a triangle has 3 sides, we can actually make 6 ratios out of the sides, right? We've made 3 ratios so far. The sine of theta was what? Opposite over hypotenuse. The cosine is adjacent over hypotenuse. And the tangent is the opposite over adjacent. We can make 3 more trig functions by taking the reciprocals of those 3 ratios, or in other words, flipping over those 3 fractions. And those are called the secant, the cosecant, and the cotangent functions. Now the secant of theta is going to be defined as the reciprocal of the cosine of theta. So whereas the cosine of theta was adjacent over hypotenuse, the secant of theta is defined as the hypotenuse over the adjacent, or 1 over the cosine of theta. The cosecant is 1 over the sine of theta. So that is going to be the hypotenuse over the opposite. And the cotangent is 1 over the tangent of theta, which is the adjacent over the opposite. Now you'll notice here that secant theta corresponds to cosine, and cosecant theta corresponds to sine. And that might be the opposite of what your mind wants to do with that. So just remember, these are actually the opposite of what you might think. The secant goes with the cosine of theta. The cosecant of theta goes with the sine of theta. Okay, so let's say we have theta equals 45 degrees. So let's draw a triangle here. Do our best to make it look like a 45, 90 triangle. So we have theta here, and that's 45 degrees. And we're supposed to find the cotangent of theta. So let's think about that for a minute. If theta is 45 degrees, we know from our previous geometry experience that the 2 legs of that triangle should actually be the same length, right? And we don't know what that length is, but let's just call it L. Then when we take the cotangent of 45 degrees, the idea then is that this is the adjacent over the opposite. It's 1 leg divided by the other leg, which is just going to give us 1. So even though we don't know the lengths of those 2 legs, because they were both the same, we're actually able to compute the cotangent of 45 degrees. Now, we're going to use the same sort of idea where we label the sides in this way to come up with the trig values, the functions of the values of the trig functions on some of those special angles that we were talking about earlier in the previous section. So what our next goal is going to be is to find the values of our trig functions for the special angles. And if you recall, the special angles were what? We had 0 degrees, we had 30 degrees, we had 45 degrees, 60 degrees, and 90 degrees. Those were our special angles. So let's start out with two special triangles. The first one being the one that we drew above. So that was a 45, 45, 90 triangle. So we have 45 degrees here, 45 degrees here, and 90 degrees for our other angle here. Okay, so now what we're going to do is just label the two sides that we know are the same, just like we did last time, right? And if we use the Pythagorean theorem, then we can find that the third side actually has to be, that hypotenuse has to be the square root of 2 times that length. And now, with that, we can actually come up with the values of the sine, the cosine, and the tangent of 45 degrees. So we know the sine of 45 degrees should be what? That should be the opposite over the hypotenuse. So if I choose one of these 45-degree angles, the opposite is going to be the length L, and the hypotenuse is going to be the length square root of 2L. So we're going to take L divided by the square root of 2 times L. The L's are going to cancel out, so we're just going to have 1 left in the numerator over the square root of 2. Now, it's traditional in trigonometry to rationalize the denominator. So here that would mean we multiply the numerator and the denominator of that fraction by the square root of 2. And what that does is it removes that square root from the denominator. So we'll have the square root of 2 divided by 2. And that's just a different way to write it. Now, historically, I think some of the reasons for doing that were probably related to approximation. It is harder to get an accurate approximation when you're dividing by the square root using historical methods. That's not such a big deal now with calculators and computers. We can get a high level of accuracy whether we put our square roots in the numerator or the denominator, but it's still sort of traditional and in certain cases important to rationalize. And so we'll typically rationalize the denominator. And another reason to do it is so that you can check your answers in the back of the book when you're working on the homework, because the book always has its answers with rationalized denominators. Okay, so our next one to compute here is the cosine of 45 degrees. And that's going to be what? That's the adjacent over the hypotenuse, which is going to be the exact same thing here. I had a little glitch there in my program. There we go. So that's going to be the exact same thing here. We have L over the square root of 2L. And it's going to cancel down again to 1 over the square root of 2, which we already know is square root 2 over 2. And so sine and cosine are actually the same for 45-degree angles. Okay, once we know those, we can compute the tangent of 45 degrees. In fact, this is what we did above, right? It was L over L. Well, we did the cotangent, actually, but the cotangent and the tangent actually end up being the same for 45 degrees, just 1. Okay, once we've computed those, then finding the secant, the cosecant, and the cotangent of 45 degrees is easy because you just flip each one of those fractions over. You take its reciprocal. Now, we've done 45 degrees. We also have 30 degrees and 60 degrees that were special angles. And we can get those using a different triangle, another special triangle, which is a 30, 60, 90. So we'll take a 60-degree angle here, a 30-degree angle here, and we have our 90-degree angle. Now, from trigonometry or from geometry, we know that if we have this side length L, um, the shorter side length, then the hypotenuse on a 30, 60, 90 degree triangle is going to be 2 times that, and the other leg is going to be the square root of 3 times L. Okay, and so what we can do now is compute the sine of 30 degrees, let's say, and that's going to give us what we're going to have L divided by 2L, right? Because this is the opposite of 30 degrees divided by the adjacent to 30 degrees. Divided by the hypotenuse is what I mean to say. And so we have, this is going to be 1 over 2, 1/2. And the cosine of 30 degrees is going to be what? It's the adjacent over the hypotenuse. So it'll be the root 3 times L divided by 2L. And we'll end up with the square root of 3 over 2. Now we can also compute the sine and the cosine of 60 degrees. So the sine of 60 degrees is going to be what? We're going to do the opposite of 60 degrees over the hypotenuse. And that will give us what? That is going to be the square root of 3L over 2L, which again is square root of 3 over 2. And the cosine of 60 degrees is what? L over 2L, which is going to be 1/2. Now you might be noticing here a pattern that these two actually ended up being the same value, and these two ended up being the same value. In fact, when we look here, when I take the cosine of 30 degrees, that ends up being the same as the sine of 60 degrees. And the sine of 30 degrees ends up being the same as the cosine of 60 degrees. In fact, the relationship that we seem to be seeing above is that if the two angles add up to 90 degrees, so let's say if alpha and beta add up to 90 degrees, then we seem to have that the sine of alpha is equal to the cosine of beta, and that the cosine of alpha is equal to the sine of beta. But would that always be the case? Let's think about it for a minute. The idea here is that if those two angles add up to 90 degrees, then they are the two angles in a right triangle, right? The two angles other than the 90-degree angle in some right triangle. And when I look at this, if I'm taking the sine of 30 degrees, let's say, then I'm taking the opposite over the hypotenuse, right? But then if I look at the 60-degree angle, notice that just becomes the adjacent over the hypotenuse. And so the sine of 30 degrees, it makes sense, would be the same as the cosine of 60 degrees if those are the two angles in a right triangle other than the 90-degree angle. So this, in fact, is a situation that does work in all cases. As long as alpha and beta add up to 90 degrees, the sine of alpha is going to be the cosine of beta. The cosine of alpha is going to be the sine of beta. And what we can do is rewrite beta in terms of alpha. So we can say beta equals what? Let's just solve for alpha here, right? So that would be 90 degrees minus alpha, or you could also write in radians that beta would be what? 90 degrees was pi over 2 minus alpha. And rewriting it this way allows us to come up with these nice cofunction identities. Now, we haven't looked at identities before in this class. An identity just means an equation that is true no matter what value you put in for the variable. So here we have sine of alpha equals the cosine of beta, but let's rewrite that as pi over 2 minus alpha. And we have the cosine of alpha is equal to the sine of pi over 2 minus alpha. And that's written in radians. We could also write these in degrees, and then we would have what? Sine of alpha equals cosine of 90 degrees minus alpha, we would have cosine of alpha equals the sine of 90 degrees minus alpha. Okay, so these are identities because no matter what value, no matter what angle we put in for alpha, these will always hold. These are always true. Okay, so one of our main goals when we're working with trig functions is going to be that maybe we're given a right triangle and we're given some information about that right triangle, but not all of the information. And our goal is to obtain the rest of the information about that triangle. And by information, I mean the lengths of all three sides and all three angles. So here's an example where we're going to start working toward that goal. It says find the missing side lengths of the triangle depicted below. So let me draw that triangle here. So here's our triangle. Try to do a right triangle here. And we are given the angle of 60 degrees here. And we're also given the side length of 6. And that's all they gave us. And they want us to find the missing 2 side lengths. And so I'm going to label those as the opposite side and the hypotenuse, right? Those are the 2 that are missing. Now, what we want to do is we want to look at what we were given and what we're trying to find. So for example, I was given 60 degrees and the adjacent side to that. So let's say I want to try to find the hypotenuse. So I'm thinking about which trig function involves knowing the angle, the adjacent side to that angle, and the hypotenuse. And once we get used to these trig functions, we'll know right away that is the cosine, right? The cosine of our angle theta is equal to what? It is the adjacent side over the hypotenuse. So let's write out what we have here. So we know that the cosine of 60 degrees is going to be equal to 6 over h. But now we just figured out what the cosine of 60 degrees was in our previous problem, right? That's 1/2. And so we have 1/2 equals 6 over h. We need to solve for h. So let's go ahead and use our cross multiplication trick, right? We're going to multiply 1 times h, put that on the left. We'll multiply 2 times 6, put that on the right. Another way to think of that is I'm just multiplying both sides by 2, and then I'm multiplying both sides by h and simplifying. And so I get h is equal to 12. So there's my hypotenuse, and I still need to find the other side, the opposite side to the 60-degree angle. All right, so now, again, I can think about what do I know? What am I trying to find? I know the angle, I know the, let's say, the hypotenuse, which is 12, and I want to find the opposite side. Well, the trig function that deals with the angle, the opposite, and the hypotenuse would be the sine function. So I'll write sine of 60 degrees is equal to the opposite side over 12. Now, before I go on, notice that I could also use the cosine here because I also know the adjacent side. So instead of using sine, I could use, or I could use the, I don't want to say cosine, but I want to say I could use the tangent, right? Because I could use the adjacent and the opposite. So I could use the tangent here as well. Okay, so I'm going to use the sine though. And the sine of 60 degrees we figured out in the previous problem was √3/2. And that's going to be the opposite over 12. And so now I'm just going to multiply both sides by 12, and I'll get 6 square root of 3 is the opposite side. And so now I have the opposite side is exactly 6 times the square root of 3. It says round to 2 decimal places as needed. So this one is where I would round probably to say that the opposite side, if it's 6 square root of 3, I'm going to put that into my calculator. So 6 times the square root of 3. And that gives me 10.3923. And so on. And I'm supposed to round to 2 decimal places. So I'll look at the next decimal place. That's a 2 less than 5. So I'll just keep 10.39. So there we go. We have our 2 sides, and one of those needed to be rounded to 2 decimal places. Okay, so next what we're going to do is look at an application of these trig functions and finding missing side lengths. So here's our first application. Let's say you have a tall object. Let's use a flagpole as an example. So here I've got a flagpole, draw a little flag on that. And let's say I am standing a certain distance away from that flagpole, right? And my goal is to figure out the height of the flagpole without actually having to climb it to measure it, right? And so what we're going to do is use what's called the angle of elevation. Now there are tools that would help you measure this. In fact, you could even just go outside and probably use a protractor to estimate the angle of elevation if you're a certain distance away from a flagpole. And so then our goal is going to be to find, using that angle of elevation and maybe our distance away from the flagpole, to find the height of that flagpole, right? And so let's try that here. So a flagpole is located 100 feet away. You measure the angle of elevation to the top of the flagpole to be 28 degrees. Now it says use a trig function to estimate the height of the flagpole to the nearest foot. So let's just draw our situation here. We're given the angle of elevation, which is 28 degrees. We're told that we are standing 100 feet away from the flagpole. And we're supposed to find the height of the flagpole, so let's call that h. So here's our right angle, assuming that the flagpole is at a right angle to the ground, and the ground is flat, right? We're making all these assumptions. But what we have then is we need to find h. We have 100. Let's figure out which of our trig functions helps us here. We have our angle. We have the opposite side that we're looking for, and it looks like we're given the adjacent side. So we have angle, opposite, and adjacent. That means we need to use the tangent function. So we'll say that the tangent of our angle is equal to the opposite side, which is h, over our adjacent side, which is 100 feet. And so when we multiply this out, we're going to get what? 100 tangent of 28 degrees equals h. Okay, now we're going to round this to the nearest foot. So what I'm going to do is I'm going to go put this in the calculator, and we need to talk a little bit about using the calculator for computing the values of trig functions. Okay, so our goal with the calculator is to compute 100 times the tangent of 28 degrees. Now, your calculator has, if you have the correct type of calculator, you have sine, cosine, and tangent here, right? It has these trig functions. But if it does have those, your calculator also needs to know whether you're working with degrees or radians. Right now, if you look right here, my calculator says RAD. My calculator is working in radians right now. So if I were to put in the tangent of 28 right now, my calculator would think that I was saying tangent of 28 radians, which is a completely different angle. 28 radians is a completely different angle than 28 degrees. So what I need to do is switch my calculator to be working in degree mode. Now this TI-30X2S, the way that we do that is this DRG button. And when I press that button, it's going to give me 3 options. The only 2 we're going to be using in this class are the left 2, the degrees and radians. And so I'm going to switch that to degrees and then hit enter. And what that does is it resets my calculator to be in degree mode. So now when I put tangent of 28, it knows that I mean tangent of 28 degrees. So I'm going to do 100 times the tangent of 28, which is now 28 degrees, which I want, and I'll hit enter, and that will give me an approximate height of, or it's giving me an approximation of the height of that flagpole. And we're supposed to round this to the nearest foot. So the nearest foot is this 3, and so when I look at the next decimal, the next place here, which is the 1, then I know I don't round up because that's less than 5. So I'm going to get 53 feet for my approximate answer. So let's go put that in. Okay, so our approximate answer here for h is 53 feet. So we were able to take two pieces of information about that triangle, two that we could actually measure, and measure or use trigonometry to find the height of that triangle. And the reason that this is so useful here is because finding that height directly might be a challenge, right? Trying to measure that directly is a challenge, but using trigonometry, we're able to calculate it using things that were easy for us to measure. Let's do one more like that. So a sailor in New York Harbor sees the One World Trade Center in the distance. She measures the angle of elevation to the top of the tower to be 10.5 degrees. Approximately how far is the sailor from the base of the tower? Now we're missing a key piece of information here that we could look up, right? The height of the One World Trade Center is actually symbolic. It is 1776, right, feet. And that is symbolic of the year that the Declaration of the Independence was signed. So we're going to use that information. The height of that tower is 1776. It says that this sailor is out in the harbor, right? We're going to assume that, everything's at sea level here, and the angle of elevation here is 10.5 degrees as viewed by the sailor at her distance from the trade center. And she wants to know how far away she is from the One World Trade Center. And so what she wants is the distance x here. Okay, now actually measuring that might be a bit of a challenge, but since she knows the height of the One World Trade Center and she knows the angle of elevation, now she can compute that using the tangent function again. So she's going to say what? The tangent of 10.5 degrees is equal to the opposite side, which is the height, divided by the adjacent side. So 1776 divided by x. Notice again, we use tangent because we looked at this and we saw we have the angle, we have the opposite side, we want to find the adjacent. So we have angle, opposite, adjacent, that's the tangent function. Okay, and now we're solving for x. So I'm going to multiply both sides by x. I'll get tangent, x times the tangent of 10.5 degrees equals 1776. Divide everything by the tangent of 10.5 degrees. So I have 1776 divided by the tangent of 10.5 degrees. One thing that I see students do a lot that is a mistake is to compute this value right here and then start doing the algebra. So they would take this, find some decimal approximation for tangent of 10.5 degrees, and then start solving for x. Now the reason that that's a problem is because you just rounded when you did that, and then you're going to take and you're going to divide by a rounded number. That's going to actually compound your rounding error. So if you do that, you're actually going to end up with a bigger error than if you just wait till the end and put your final answer in the calculator all at once. Now this is going to become more and more important as you move on in mathematics and as you work in applications where you need lots of intermediate computations before you come up with your final answer. And the more that you can wait to throw everything in the calculator to the end, the better, right? Because the fewer times you'll have to compound that error. So your goal should always be, if possible, I'm going to take and I'm going to symbolically solve for my final answer like we did here, and then I'll plug that whole thing into a calculator or a computer at the end to get the most accurate rounded number. So currently this answer, when we compute it, is going to be in feet, right? Our original units here are in feet. But when we look at the original question, it says round to the nearest tenth of a mile, which means we need to take this answer and we need to convert it to be in terms of miles instead of feet. So right now, our units are feet. And so what we're going to do is we're going to multiply by a fraction where we're going to convert from feet to miles. And that conversion is that 5,280 feet are in 1 mile. Right? And since I want to get rid of the units of feet, I'm going to put that 5,280 in the denominator. And since I want to move to miles, I'm putting miles in the numerator. And so what that's going to do is it's going to cancel the units of feet and give us the units of miles. So as a single final computation, to find out our answer, we're going to take 1776. We're going to divide by the tangent of 10.5 degrees, and that's going to be multiplied by 5,280. Now, like I was saying before with rounding, what I want to do is put all of that in my calculator at once at the end, and that will give me the best approximation that I can get. Okay, so let's go to the calculator and do that since this one's a little bit more complicated. Okay, in order to put this one correctly in our calculator, what we need to do is we need to make sure that everything that's supposed to be in the denominator ends up in the denominator there. So I had 1776, and I'm dividing by everything else. I'm going to open a set of parentheses. I'm going to compute the tangent of 10.5 degrees. So again, I better make sure I'm in degree mode when I start this, right? So I'm going to compute the tangent of 10.5, that's in degrees, and now I'm going to multiply that by 5,280 because that was also in the denominator. Now, I opened a set of parentheses for the denominator. I need to close that set of parentheses for the denominator. So I put the entire denominator in a set of parentheses to denote that I want everything there to be in the denominator. Okay, and now we're going to take that, and we got, what, 1.814, and we're supposed to round this to the nearest tenth of a mile, so that's going to be 1.8 miles. Okay, so since I rounded, I'm going to change this symbol to an approximation symbol, and we have 1.8 miles. Okay, so she's a distance of approximately 1.8 miles from the World Trade Center.